Hello, good afternoon. So welcome to this session where we are going to discuss multi-threading. But before we get there, let me tell you how this is going to go. Yes, it's going to be about multi-threading, but we will look at a particular application of multi-threading here. And the example at hand will be sorting a large collection of numbers to start with. And from there, what we can do is I got a deck of playing cards here. So we'll try to create a class for this, a new data type to represent playing cards. And then we will create a lot of cards, like not physical ones, but virtual ones. And then we are going to sort them. Okay. We're going to sort them using one of our well-known sorting algorithms. But when we do that, be it the case for sorting numbers or be it the case for sorting playing cards, we will see that the problem there is that it takes a lot of time. If there are a lot of elements to deal with, yes, of course, it will take a lot of time. So the idea over here for today's class is to see how can we speed up the entire process. And then we will realize that since we have a lot of processing cores in our system, not just on the computers, but also on our phones also have a lot of cores these days, 6 cores or 8 cores. We have a plenty of them available. So rather than giving one processor core the entire job, why not employ all of them, like all the available ones? So in order to do that, we will divide our task into smaller parts and ask the cores to take care of them. And when we get the result done, is there a way that we can do this any better? Like to give you a quick little example, if I start to sort all 52 cards in here, it will probably take a lot of time. But if I'm given, say, only a few of these cards, then I can sort them just by myself. Well, I can sort the entire thing just by myself. It's going to take more time. But if I'm given fewer cards, obviously, it takes less time to sort them. Okay, so that's the idea, and we'll see how we can do that. So this is going to go on in multiple stages, this entire talk, or the session rather. And throughout the entire thing, we will keep on improving the way we are writing stuff. Okay, so to start with, we will just write a tiny piece of code which only sorts numbers and nothing much. But yeah, from there on, we'll see how far we can go, right? So let me share my screen. This is our online class number 13. Yeah, and like I said, we're going to talk about multi-threading here. And the algorithm that we're going to use to demonstrate multi-threading is going to be insertion sort. So initially, it's just going to be a regular insertion sort code, which does nothing but sorts an entire range of numbers. Like we'll have a lot of numbers to sort, and we'll see how much time it takes. And from there on, we'll see how we can take it to multi-threading, how we can get all the available processors and use them to speed up the process. Okay. So that's that. Let me get a project ready. And while we are at it, I think I can pause the video because there's nothing happening here. Okay, so we're back and I got my ID running now. So we're going to create a new project. It's going to be just like any other project that we created, a Maven project to start with. So nothing fancy at all. There is not going to be any UI component here, not for today. And let me give it a name. So we'll call it multi-threading demo. We need the artifact coordinates, or we could just leave it the way it is. But like our other projects, I want it to have the same thing. So this is for Southeast University students. That's why bd.edu.aceu. And the artifact ID is already set. So we'll hit finish and we'll have our project ready. Okay. So before we go for anything else, let me set up the essentials, like for settings, the compiler version. So Java compiler, I think by default it would be set to JDK 1.5, but it only appears when you start writing code. So let me get there. So let's create this project first, the package first. Our package is going to be pd.edu.acu multi-threading demo. All right, so it's a long name, but yeah, let's leave it like that. And to start with, I'll just create a main method within a main class. So that's our entry point. And you guys are quite familiar with this, that the way I do it here is I just create a constructor for all the console applications. I create a constructor, and from public static void main, just instantiate the class by creating an object here, and it says new main. I forgot to put in void. So public static void main string args, and that's that. And let me just test this out. System.out.println, I'll say hello. And if we now run this program, it should work. Okay, so release version 5 is not supported, and this is what I was expecting, and that's what I tried to fix. So if you go to settings, now that we have some base code available, and we have this module, this this bytecode for this one, I will choose my compiler version, or we could go for something a little bit lower, but definitely higher than JDK 5. That is just so backdated. So that's that. That's one fix. And for project structure, there were two things that we had to play with. Yeah, well, actually, one thing right here. So switch expressions for JDK 14. Yeah, now that we have that set, if we run our project, it should show us hello, and that's all there is to it. Okay, so yeah, it's pretty much up and running. We got our main, and that main only says hello. Now, in order to get our data, what I'm going to do is I'm going to create a separate class, which is going to give us our input data. I could do it right within the main, but I like to keep things separate. And since we're getting a little bit mature as we are progressing throughout the course, we should make a habit of this, right? So this is going to be our data generation service. Excuse me. And all it does is it generates data for us. Okay, data in the form like what do we expect? We expect to get some numbers, right? Let's say the numbers are going to be integers. Well, I'll just call it n, right? So get data, and this is a bad practice, but let me just call it this way: get integer data, so that we know that we're returning an array filled with integers. And the reason why I'm doing this is if we choose a different data type, maybe we'll have a different method for this. Although there are better designs for this, and we will get to a point where we will see that this is probably not the right way to do it. Okay. So this data generation service, it generates data for us. That's all it does. Okay. And for now, it gives us integer data, which we will get, and then we will sort them somehow, and we will print it out on the screen. So in order to do this, first of all, we need an array. and the array will have n elements in it. We will go through each and every one of the indices and fill this with random data, right? So for int I equal to 0, I goes all the way to something less than n. Well, 1 less than n, not something. And this is where we're going to get random data. Now, in order to do that, I could do math.random, but I could also use, excuse me, the random class. The reason why I'm picking random in here is we can call random dot next int, and then we will have integer within a particular bound, right? So let's say all my numbers are going to be from within 0 to some range, right? And this is probably a bad thing to do, but let me do it anyways. So let's say my numbers are my numbers can be this big. Oh, by the way, these underscores, they can help you separate out the zeros or anything else in a number. So we can't really write 1 comma 0 0 0 comma 0 0 0. We can't do that, right? But using underscore helps with the readability of the code. I think it was introduced either in JDK 8 or JDK 9 that we can now do this. Okay, so now we can have a random integer that goes from 0 to less than 1 million. Okay. So what we can do is we can put this into our data array. Data at index I is going to be number. And now that we have filled out the array after running the entire loop, we can return data. It's as simple as that. Okay. So if you go to main now, right within the main method, this is a bad place to do this, but let me do it anyways. We can have our data generation service. We can create an object out of it. Okay. So this is where we're going to say data generation service dot get integer data, and let's say I just want 10 elements just to see how it looks like. So, and then we can yeah, have an array. Okay, just going for a short name here. And then we can print them out. Since it's only 10 numbers, I can print them out all in one line. All I got to say is print it out using arrays.toString. So yeah, we got the data. And if we hit run now, then we should be able to see the entire thing in one go. Okay, so yeah, we got all the elements like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we're getting data. Now I did it here. I did it right in the main, and we can see the data. It's not the right way to do it. Okay, we learned this before that we should be writing unit tests to make sure that the data generation service works properly, but our target for today is something different. And although we're going to look at so many different things, I think it's probably better to stay on track and skip the unit testing for now. Okay, so what I'll do is something I have shown you already. Java knows how to sort numbers. So what we can do is we can just say arrays.sort data. So everything will get sorted. And then we can copy paste this line again and print this out after sorting the numbers. So we have one printing before we sort the data, and then one after. Okay. So the next time we run this program, it's going to give us something different, but yeah, this is where we see that everything is sorted, right? Now, you may wonder, like, we already have a sorting algorithm in place and it's already implemented. So what's the big deal? Why are we trying to write our own sorting? There is absolutely no reason why we should do it. No practical reason, but we're here to learn multi-threading, and this is one of the applications that I wanted to show you, that it can actually speed up the entire process. And that is the reason why I want to show you that you can do it faster if you use multiple cores available on your computer. Okay, so even though the sorting implementation is there, we're just not going to use it for now. We're going to have another class in here that does the sorting for us. Okay, so we will do something like we'll create another sorting service method where we will just call it public void sort. And within that, let's say we'll pass the integer data, and something magical will happen here. Something magical like arrays.sort for now, just to show you that this works. And we will sort data that gets passed in here. And probably there is no reason to return it because, well, we could if we want to. Right, only in case you want to chain this call with some of the calls. So we'll return data just like this. So from within main, what we're going to do here, we got data generation service here, and now we also have the sorting service. We're going to create an object for that new sorting service. Okay, and now what we can do, we can eliminate arrays.sort. We'll say sorting service.sort and pass the data. So this should still work. If we go and hit run, this should still work. It's just that we wouldn't know what kind of sorting is happening in here. Okay, so yeah, it still works. It does proper sorting, and it uses arrays.sort, which is something we are going to change pretty soon. So this thing is what we're going to change with our insertion sort. And I have the insertion sort code in here, which I want to keep on the side so that I can follow it along while I'm writing code here. So let me keep it always on top and get a little bit of room. All right, so yeah, only 8 lines of code with some comments in there, so it shouldn't be too difficult. All right, so this one says for j equal to 2 to the length of array, but you got to understand that the way this algorithm was presented, and by the way, this is taken from Introduction to Algorithm by Corman, Liserson, Rivest, and Stein, the third edition of the book. So what we're going to do here, instead of going from 2 to the length of the array, because the indexing starts from index number 1. Instead of doing that, we're going to start with indexing 1. J is going to be less than data.length, and J++. I'll stay true to the code in itself, and this is going to bother me a lot, but I'll do that anyways. Like, the thing that bothers me right here is the name of the array. In Java, we use lowercase names, but I'd have to change that. I hit F6, Shift F6 to rename this. So I'll call it A, just to match with the pseudocode that we got here. So then what we need to do is we have to have a block of code underneath the for loop. So that's that. Since we're working with integer data, this is going to be the key. It's going to be AJ, not Anuntu Jalil. It's just index J of array A. Then we have int I equal to J minus 1. And then while I is greater than 0, that's what it says here, but we're going to go 1 less than that, right? So it can reach up until 0. And AI is greater than key. What's going to happen is AI plus 1 is equal to AI I equal to I minus 1. What else? We're done with the while loop, and then we say AI plus 1 is equal to key. All right. So within the main, if we go back, and now we don't have our arrays.sort call, but it should still work. Assuming that I wrote it right, I copy pasted the pseudocode into Java code. It was a bit of a straight translation. So it looks okay, I guess. And it takes a little bit of time. I don't know how much time it takes. And the way to know how much time it really takes, it's quite easy. We can do a start and stop timer. The way we do it is we call system.currentTime millis to start. And then stop is system.currentTime millis again. So we are taking snapshot of time at two points in time. And then if we subtract that, we will get the time difference in milliseconds. Okay. So we can do something like this, system.out.printf. I'll use printf so that we can have fractions, a fixed number of milliseconds after the seconds. So we can say time taken. Let's say I will print 4 digits after the dot. Okay. This is where we say stop minus start divided by 1000. Now, if I do that, stop is a integer data type, like it's long, but it's a whole number, right? So we have stop minus start. The resultant thing is going to be a whole number again. And if you divide that by 1000, which is another whole number, it's going to use the integer arithmetic part of the ALU. It's not going to involve or invoke the floating point arithmetic. So the result is going to discard any sort of floating point calculation that has to happen here. So even though you get like 0.5 seconds, it's not going to show you 0.5 seconds. It's just going to show you 0 because it's going to do a integer division. Now, to force it not to do it, we can just change one of the operands to say that this is going to need floating point calculations. So I did that bit, and let us run this thing again, just to see how much time it takes. It's probably not going to take much time at all, just to see how it looks like. Yeah, time taken, nothing at all. So let me comment this out because I'm not really interested about the data in itself, right? So I want to see the time because the sorting thing probably works properly. So instead of working with 10 numbers, let's say we work with 1000 numbers. Maybe that takes a little bit of time, or maybe it doesn't. So yeah, it doesn't even need 1 second. It takes 0.01 second. So let's bump it up even more. So let's work with 1 million numbers just to see if that makes any difference here. Now it's taking time, right? And it is probably taking too long. Yeah, that was probably too high of a jump. So allow me to stop this. I can do it here, or I could do it there. So baby steps. So let's go with 10,000. Yeah, insertion sort, it takes order of n squared time, and that's why it was a really big jump. Now, it's not going to be linear. Going for 100,000, it's also pretty big, but I want to go into seconds, not just milliseconds. That's why I want to bump it up a bit. So it takes 5 seconds. Not too bad, but it's still quite a bit of time. So we'll see how we can improve on this now that we have the sorting thing working at least. Can we make it run faster? Okay. So that's one of the things we got to try. We will bring out multi-threading real soon to see how we can split the task into multiple parts and make sure that this thing can run faster. Okay, so let me stop recording for a little bit and get back on it again. Hello and welcome back. So I had to take a break for shower and lunch, and here we are. I came back a different person. I don't know if you can tell, but yeah, it's me, a different person. The reason why I'm telling this is because I had this revelation. And I realized that I got to practice what I preach. So in the previous classes, and even before, right at the beginning of the semester, I kept on saying that we should write unit test, we should write unit test. And here in the first part of this recording, what I did is I just skipped that bit just to save time, or I figured that it's going to be a little bit distracting. I'm moving away, which is true actually, but let me do that. Let me go through the entire process with unit testing and all. It's going to take more time, of course, but it's probably the right thing to do. Okay, so that's one thing, and I should also follow the other things that I was talking about in the last few classes. Like I talked about interfaces, I talked about enumerations, and I also talked about polymorphism, how having a good design helps with that and all. So I'll bring a little bit of that into today's discussion as well. I realized that the entire talk was supposed to be on multi-threading, and I'm actually going quite far away from that track. But maybe it's for a good reason, and definitely we'll come back to multi-threading in a bit. So it's going to be a pretty long video, I think, if it goes on like this. But yeah, let's do that. So let's go back into my screen. Here we are. And this is the last thing we did. So we have this get integer data right there. We have this sorting service that sorts the data. And before we go any further, what I want to do in here, let me show you, is that this sorting call, this insertion sort, it sorts the entire array. Okay. Now the problem with that is that we cannot just say that, well, to give you an example, that I don't want to sort the entire deck of cards like that. Maybe I want to split this into, say, just two halves, all right? And give it to two different person to sort so that they have less to deal with, because it's just half the task it was before. Now, theoretically and also practically, it would mean that it would take less time to sort this thing. Once we get the sorted cards back, we can put them together by some merging process. So I stole some more pseudocode from the Introduction to Algorithm third edition book. So we have this merge call, and it really helps with a situation like this where you have two subproblems, like two sorted arrays, and you want to merge them together. Okay, so this is what we are going to look into through the merge process. But in order to apply merge, what we got to do there is that we'll have to have the partial array sorted. But we are given a large array to sort with, right, to sort. So in one way or another, what we have to do is we have to be able to sort a particular section of the array, not the entire thing. That would allow us to say that, let's say we are going to sort the first half of the array and maybe sort the second half of the array and then merge them together. So we got to change the definition of sorting in here to allow for a from index and a to index like that, okay? And that would mean that our existing code would break, which is not really a problem. We got to fix that anyways. And we can say, just to be consistent with the entire thing, is that we are going to sort from 0 to all the way to the last index of the array, which is data.length minus 1. Okay. And it's not going to break our code at this point because we haven't done anything in here. It still sorts the entire array. You see, from index and to index, they are never really used, right? So that's what we are going to do. It is actually quite an easy fix. If you think about it, it's actually quite an easy fix. If you look at the indices that we have in here. So first of all, when you look at one, it's the second element from where the sorting would start, because the very first element, if it were just a single element, that element is already sorted. There is nothing to do, right? So instead of starting from 1, where we actually start from 0. So this looks like something like this, right? And so instead of doing that, what we could say is that instead of 0, start from index. So that's the very first change. And the second change we want to make here is that we got to make sure that it goes all the way to the last index, but a dot length is 1 after the last index. So what we say in here is that instead of going that route, let's go to to index plus 1, because the from index and to index, the way we are writing this, it's going to be inclusive, not exclusive. So it's actually closed. And yeah, these are the two changes that we have made. Now, is this good enough? Right, that's a question. We got to find that out. I know for a fact that this is not good enough, but that's a different story. So the easiest way to test this out, whether this is good enough, is to write some test. Why not do that, right? Since we already have that facility. We are going to create some test. And I want to create a test for the service only. And it's going to be probably a good idea to separate out the service and the other rest of the stuff. So we could have something like this: VDA do SEO.multithreading demo.service is a test package, and within that we're going to write our test. But at the same time here, we should also have that separation and create packages for the services that we are creating. So all these service classes that we are creating, they should fall under service, and we can refactor them. Okay, let's continue with that, and then we will fix it. So what's getting inaccessible? Get integer data. Yeah, that's because I didn't make it public, and when they were in the same package, they were still accessible, but now they are not. Okay. So now that's sorted out, let's create a test. So we're going to call this sorting service test. This is where we test our sort. And what this is doing, well, this is for int sort, and we pass the array, we pass from and to index. Okay. So when we write the test, let's say public void test. Let's say I want to write a test that sorts the entire array. Okay, so how do we do that? I'm going to include JUnit 5.4. In the class path, it's not included by default, so that's that. Okay. So with that in place, what we can do is we can create an array to start with, and then see if it properly sorts the entire thing. So one way to do that would be to create this thing, and I can generate random stuff, and based on that, we can try this out. But since it's going to be an unit test, I think it's probably be easier if we are able to look at exactly what the data is and what's happening and what's expected and whatnot, right? So let's create this really simple example. Let's say we have this random array where we have some random numbers. They don't have to be single-digit numbers, really. Okay, I'm just creating this random array thing. Okay, and then I want to create a sorted array. Okay, the sorted array is going to be pretty much the same thing, but the elements, they are going to be, well, properly sorted. So the sorted array can be an exact copy of this thing. Let me make sure that we have this. So how do we write this? New int, and the size of the array is going to be random array size. It's going to be of the same size. So now that we have these two arrays created, I have to copy over all the elements that were there in the random array into the sorted array, right? So we can call arrays dot system.array copy rather. System.array copy. I have used this before, I think in your class, or maybe I haven't. Either way, you learn something new, I guess, if I haven't. So the source over here is random array. We start at index 0. We copy it over to the sorted array at index 0, and then we're going to copy the entire length, right? So random array dot length. So the whole thing gets copied over. And then we got to sort it. Arrays dot sort, sorted array. Okay, so now that we have this sorted, we have this random array, and I haven't touched it. It's a separate copy, and sorted array is actually the sorted version of it. So if our sorting algorithm works, what we can do is we can call our sorting service, right? So let's create an instance of that. Sorting service equal to new sorting service, and then we can call sorting service dot sort the entire array. So random array, start from index 0, go all the way till the last index, which is length -1. So if everything works fine, we should have the entire array sorted. Now, in order to test this out, this is now quite easy to do, is we can run a loop through the entire thing to test this out, or we can just do one assertion and say assertions dot assert equals the expected thing is the actual sorted array. And this random array is just going to be the same. So we can test for that. If this assertion passes, then I think we are good to go. Let's test this out, okay? Let's test the sorting service test. Why do I get this? Release version 5 not supported. So let's look at project structure. If we have changed anything, no, we didn't, but this one got changed. So let's flip it back to JDK 14. So that's that. Java compiler switched back to 1.5. You know, the assertion failed because, oh, I see. It was a mistake. Yeah, I can't really compare it this way because I have to go element for element. So I can do two assertions that the length of these two arrays, they stay the same before and after sorting. So it's kind of pointless because we wrote it to match. I've created the sorted array to match the exact length. So it's not going to be anything different, that's for sure. But let me put that in place. And then we can run a loop to go through the entire array. So for int I equal to 0, I less than random array.length, I plus plus. And here I want to do the assertion. Assert equals, they should have a 1-for-1 match, right? So the expected output is the sorted arrays, index I, the element at index I. It should match with random array, which is the calculated one at index I. So yeah, 1-for-1 match for the entire thing. If that thing passes, then I think we are good to go. So yeah, that at least works. Okay, so let's take it for a spin. Let's write another test. But this time around, we want to the sorting for a partial array. Okay, and let's say we copy the entire thing. We have exactly the same thing. We're going to sort it, but I don't remember whether sort has multiple variants. No, not this one, but yeah, I think we have a from index and a to index. Yes, we do. And to index is actually the last index. Oh, but this is exclusive. So this is a little bit different here. Notice that from index is inclusive, but to index is exclusive. This is arrays code. Let me be consistent here. Let me be consistent with this. They follow a good standard. So I don't want to get out of that, which I already did, but it was a mistake to do so. Let me fix this now before I go too far into it. So when we pass this, since this is exclusive, the to index is exclusive, let me leave that out, okay? And what else do we have to fix? Yeah, since this is exclusive, we can exclude that one. So that's the other change. Where else do I need to change this? The test itself, right? So when we were calling sort the entire thing, instead of doing -1, so I'll go for the entire array. That's for the full array, and this one, of course, needs some changing, which we are about to do in a bit. So for the full array, this should be okay. Okay, for the partial array, we got to say from where till what point I want to sort. So let's say I want to sort from this is 0, 1, 2, from 3. Okay, so from index 3, 4, 5, 6, 7. So let's say till 7. So only that bit would be sorted, and the rest is not going to be sorted. Now, if I leave it just like this, it's probably not going to work, because our sorting service is going to sort the entire thing, even though we tell it to sort a different part. And let me be nice here and write these down. So this is going to be 3. It's going to be 7. And we can write this out. So from index, and we will go all the way to index, and it's going to be from index, and instead of going all the way, this is going to be to index and no -1 anymore. Okay, so look at this again. We have the random array, which is the random thing, and we have the sorted array, but within that sorted array, only part of it is sorted. The other thing is not sorted, right? So that's that. And the final thing that you need to notice here is that if our sorting service works properly, so from index all the way to index -1, only that bit is going to get sorted. Okay. And after that, we have the sorted array, the original array, where we have a partial sorting with a call to Java's arrays.sort for a partial sort. And then we, on the other side, we have our sorting service, which also sorts with insertion sort, but it also does a partial sort. So both these arrays, they should match one for one for each of these elements. It should match. If it doesn't, then obviously there is something wrong. Okay, so we got to figure that out if this thing actually works. And I forgot to do this here, but I think it would be a good idea to print out these two arrays so that we can manually see something in our screen. This is not always essential, but let me do that here so that we have some visual cues. So arrays.toString, we have the random array, and we have the sorted array, right? And what we can do is we can actually print it out here before sorting. All right, so we have the original array, and this is before sorting. Oh, I mean, that copy is good enough itself. All right, so random array is what we are going to look at. And after sorting, they should match, right? So these two things, they should match. So this is going to be initial array. This version is sorted by arrays.sorted, and I'll have another one sorted by the service call. All right, so, and let's try to align them so that it's easier on our eyes to check. Okay, so that'll do. I think it would help us track what's happening here. So we can print this here, this guy, and the other two is what we are going to print after we are done with sorting, but before the assertion starts, because if the assertions fail, then we don't get to see the output. Okay, so fingers crossed, and let's hope for something best, something good, not even best. Okay, so one of the tests, it passed, the other one failed. Now, for the one that passed, if you look at it, we have this initial array, and we are sorting the entire array, and yeah, the arrays.word sorted one gives the entire sorted thing, and so does the service sorted one. However, for the one that we just wrote, where we are doing a partial sort from index 3 to something less than 7, I guess, yeah, 0, 1, 2, 3. So up until this point, this is where we are starting to sort 3, 4, 5, 6. These 4 elements, they should be sorted, right? So what we get in here is not the right thing. So this is the initial sorted one, and the random array gets sorted. Let's see. What did I do? I call arrays.sort on the sorted array. And the random array is one that we are sorting with the other one. All right, so this is actually the other way around. Arrays.sort sorted array is the sorted array, rather. And the service one, it's sorting the random array. All right, so that's where I made a mistake. And I should make the same correction for the other one as well. Sorry about this, but I didn't notice. Nope. Okay, so let me do this again, and it's getting quite dark in here. Not talking about the TV series. So this one's all right. And starting from index 3. Okay, now it makes sense. 3, 4, 5, 6, and 7. Okay. So it sorts the whole thing, right? Um, this entire range. 3, 4, 5, 6. These 4 elements should get sorted, and that's what you get. 1 is less than 2, and 3 is less than 6. So this part is sorted, but after that, it didn't really touch. Although it's kind of misleading here. So let me change the numbers a bit. So 9, 2, and 9, 2 up there. You know, like the last few elements, they're already sorted. So we probably get a fake sense of relief, I think. Yeah, I don't know why I'm making changes like this, but hello. Okay, now this looks better, right? So we have this little bit of change in here. And yeah, so till this part, everything looks okay, but see the change? For the service sorted one, we are actually ruining things in this part. Okay, so this is not right. And the reason for that, if you look at the code itself, we are going all the way to 0. We are allowing for this, but it should go all the way to from index, not more than that. This is the other change that we got to make, understanding that 0 stood there as the starting point. So since we're not making that change to accommodate this, that's why our test failed. And this is a good check, right? Now that everything passes, you have a better confidence about the entire code that you wrote. And previously, it would just not be possible. You can test it with different set of data, and you can run the test as many times as you make changes to the code. It should still work. Okay, so that was something quite necessary. And now that it is in place, can we have 2 different parts of the array sorted, and then say that if something magical happened, right? So in order for that to happen, let's have a quick look at this merge algorithm. So in merge, what we expect is that we are given an array, and the indices from P to Q, and Q plus. Okay. So yes, P to Q. We got an array A, and we want to sort from P to R. Okay, and Q is the middle ground. So we are going to sort an array from P to Q first, and Q plus 1 to R. After that, we are going to merge with this call. So P to R is, P to Q is 1 point, one of this. Where's my cursor? Yeah. So P to Q is 1 part. And then right after that, Q plus 1 to R is another part. Okay, so we are going to sort these 2 subarrays and make sure that the entire thing is sorted. Okay, so that's how merge goes. And now that we have our code ready, can we take it for a spin, right? And this is easy to show now that I have this partial sorting in place. what I will do here is I will copy this again. Okay. This sorting, yeah, let me give it a different name. I'll call it test sorting 50-50 array. It's a bad name, but it actually gives you the right sense. So I'm going to sort half the array here and another half over there. Okay. So the same thing again, but here we got sorting service, right? So instead of having from index and to index here, we are going to go all the way. So we say sorted array dot length. So that's that. And in here, we want to go from 0 to random array dot length by 2. Okay. And this is where we go random array dot length by 2 plus 1. Okay, because the other thing is part of the other array to the entire array, the rest of it. Random array dot length. Okay. So yeah, everything should work properly. Yeah, I never really printed the length of the array, and I think we should. So the array length is going to be what? Sorted array dot. Now, what are we working with? The random one. Although they're the same thing, let me do it properly. And I have an intruder. I think this thing looks okay. We will have a test fail. Yeah, that was a bad example. So 50-50 thing fails, but we can fix that actually. So I'll do exactly the same thing. Sorted array dot length by 2 plus 1, and this one goes all the way. Right, so no more of that. Now, if we run this, all the tests should pass, assuming we did things properly. And if not, I'll have to shoot myself on the foot. Okay, I got saved. So if you look at this, we had 11 elements, and by the look of it, the first few elements here, the first half got sorted separately, and the second half got sorted separately. So we can do this with arrays.sort, and we can also do it with service.sort. Now the target over here, since we have these two halves sorted, can we merge them together? Like imagine that we have two decks of, well, one deck of cards, but split into two halves. Can we flip them together, like merge them together, not flip them together? So somehow, not like a shuffle, but can we put one card into another one and have them filled in? This is not how we do it, though. What we do it when we merge two split things, if they're already sorted, we look at the top cards. So we have 6 in here. This is a bad example. You know, why did I come up with that? So we have 6 in here, and we have 7 in here. Since 6 is less than 7, 6 should come first, and then should come 7. So we'll look into that and have a look at the merge pseudocode that I stole from Introduction to Algorithm, and implement that in our code so that we can have something running in here. Okay, we're still writing pretty much sequential code, but it's for a good reason. I think if you understand how the entire thing works sequentially, then it's easy to parallelize it from there or use multi-threading from there. Okay, so let me stop recording this one and start another session where I will talk about the merging process. And once we get to that point, we can probably take it for multi-threading. The target is then, once we have this entire thing written for sorting, let's say, integers, we will change this to make sure that this code actually works for maybe strings, it maybe works for doubles, or perhaps for shorts or any data type really, like can we make it generic? That's what we are going to figure out, okay? So we'll do that. Okay, so that's so far the plan. And well, when we are testing for generic, this is when I will bring out the card example. And that's the entire reason why I got this deck of card with me. And also for a little bit of distraction for myself, because I get bored, because you guys are not here. Yeah, you should be here. Okay, let me stop this. Okay, we are back, I think. I had to take a break, and actually a rather long one, it seems. So yeah, that's that. But here we are. Now, before I go back to sharing the screen, let me show you what we have at hand right now. To illustrate the process, what we're going to go through, what I did is I picked some cards from the deck over there. And I only have two different suits in both my hands. On my right hand, we got the spades, and on the left hand, I got the diamond suit. And on the left side, I think, let me count. I got 1, 2, 3, 4, 5, 6 cards, and on the right side, I got 5. So they're not the same, but yeah, it doesn't matter. I mean, they're close enough. And right now, this is not sorted. Okay, let me see if we can see the all the cards here. It's not clear, I guess. What's this? Okay, all right, I think we can. It's flipped for me, and that's a bit of a problem. So we got 10, 5, 3, 8, 6, and a 9, right? Yeah, this is not sorted, okay? So first of all, let us imagine that we are given an array where all these cards are there. And after splitting this up, excuse me, this is my left half. And I'm given this task to sort this using insertion sort, for example, okay? So we'll start with one end. We got 10, and the next card, well, 10 in itself, this is sorted. No problem with that. Then we got 3, and the question we're gonna ask is that we'll start with this one and see, well, we got 5, not 3. So we have to ask whether we put 5 in front of 10 or after 10. So of course, 5 has to be placed on before 10. So it goes there, okay? Or how do I show this? Yeah, I think this would do. It's easy for me to see. And the next one we got is 3. So we start with this, and we ask, is 3 less than 5? If so, it stays right here. And that's the case. So you got 3, 5, 10 properly ordered. And the next card we have is a, what's this? A 9. So we try to place it here. Now it doesn't work. Then we shift it over, see if this is greater than 5. Yeah, it is. So if shift some more and see if it is greater than 10, then it would be placed down here, but it is not. So it gets placed before 10. So we have a shift in here. So that's insertion right there. This is how it's working. The next one we have is a 6. So is it greater than 3? Yes. Is it greater than 5? Yes. Is it greater than 9? Answer is no. So after 5, we insert this, but this is before 9. So yeah. So far so good. And the final one is 8. Less than 3? No. Less than 5? No. Less than 6? No. Less than 9? Yes. And here we insert this one. So let me try putting everything together so that I can show you one final time. And it's difficult to hold cards like this, I guess. Or I think I can fan them out a bit. a little bit better. So here we go. 3, 5, 6, 8, 9, and a 10. It was pretty shy, that 10 one. So this is done. And the same thing we'll do over here, but I want to go a little bit faster with this one. Got all these cards, and we have to sort them with insertion sort in the same process. So this is where you can start off with A's and then try putting them in the right place using insertion sort. I'm going to do that, but let me do it by myself because it's the same process, really. Again, insertion sort is a really handy one to apply for ordering your cards when you're playing cards. Although we won't probably call it insertion sort, but that's exactly what it is. So here we got all 5 cards sorted using insertion sort. We got a 4, a 6 and a 9, a jack and ace. Okay, so this pile is also sorted. Now, what is going to happen is that since we are looking at these 2 decks, okay, the left one is the red ones, and the right one is the black ones. Now, at any given time, we're only going to look at the top card here. Okay, and from here, just by looking at the top 2 cards from both these sides, we will make a decision which one is smaller, and then we will pick that and put it in the original array. So here we got 3 and a 4. Out of these 2, 3 is smaller, so we put 3 in here. Then we got a 4 and a 5, and 4 is smaller, so we put 4 in there. We got 5 and a 6. 5 is smaller, so we put that down. Then for these 2, we got a 6 and a 6. And right now, there is no way to tell which one is smaller. But we have to come to some sort of a conclusion, right? We have to define some sort of logic that says whether the red ones are going to get placed first, or is it the right ones? And for our case, let's just define it that the diamonds are smaller than the spades. Okay, it makes life easier. So in that case, this 6 actually goes before the spades. So there you go. Now we have 8 and 6, easy call. 6 goes down here. Got 8 and 9. Of course, it's 8. We got 9 and 9. Since the red ones, the diamond ones, are smaller, down it goes. We got a 9 and a 10. 9 goes down. We got 10 and a jack. 10 goes down. Then we are left with 2 cards. Here it is empty, nothing left. So jack and ace, and everything is sorted. Let me see if I can arrange all these cards in my hand. It's going to be a little bit difficult, but let me try anyways. All right, so yeah. Yeah, finding them out. All 11 of them. It's being a little bit of a challenging task for me, but yeah, I think I'll give it a try. Almost there. All sorted. This is what we're going to implement. Okay. So we're going to go into the screen share and start stealing code from the pseudocode and implement that right into the, steal code from pseudocode and translate that into Java. That's what we are doing anyways, right? So let me start another session for this. Okay, I think I'm back. Let me share the screen. And here we go. So the plan is to, where's our sorting service? Yeah. The plan is to put another method in here, which says public int. We're going to return the array. And this is going to be our parallel sort. And we have the array. And it would look much like the merge sort. So in merge sort, what we have here is that we have an array A, and we have P and R giving us the two boundaries, the left endpoint and the right endpoint of the array. So what happens is that if P is less than R, in that case, we find the middle point. We call merge sort to recursively sort the left half, and then we call merge sort to recursively sort the right half. And once both the parts are done, only then we would call merge to take care of the merging part. I'm not going to go into a whole lot of detail, but you guys should know about this. You see, the base case written here says if P is less than R, only then you stop. So that's going to get violated when P is equal to R, not before that. And when P is equal to R, that means that both the markers are on the same cell, which means that you have only one element to sort. If you have a single element to sort, so for example, I got a single card to sort, it's already sorted, nothing to do, right? That's why this is the base case. So is this a good implementation then for merge sort? The answer is no. The reason for that is because if you want to go down to a single element, if you keep on dividing it, this is a divide and conquer algorithm. If you keep on dividing it till you reach that point, then it's just going to take too long. It will be a lot of recursive calls to process. It would mean that your call stack is going to grow bigger. And if you don't have enough space in your stack, you're going to get stack overflow. Not in a good sense, right? It's not about the site. So yeah, what do we do then? Well, we find a sweet spot. What we have seen before is that insertion sort is not really bad. It's just that for a large number of elements, it is particularly bad because in the worst case, insertion sort takes big O of n squared time. I haven't shown this thing here. This is not a course in data structures and algorithms. So I haven't talked about that. But I guess you guys know this already. So yeah, we can't use insertion sort for large number of elements to sort them. So what if we can go for smaller size? Like let's say an array of 100 elements or maybe 1,000 elements. We'll have to find that sweet spot till what length insertion sort performs pretty good. And the merge sort is actually slower in that range. So once we figured that out, we will let insertion sort take care of the smaller sized arrays. And that's what we will use in the base case right here, instead of saying P is less than R. And when P is equal to R, you stop, not till that. If we find out that it works well for 1,000 elements, then we will take care of the 1,000 elements. We will not use merge sort to divide it any further. We will just take that and run insertion sort on it, okay? But I'm not gonna go that route here. Now, this is going to be really very simple. I will imagine or assume that we have only two parts to sort. The left half will get sorted separately, the right half will get sorted separately, and we will merge them together, okay? So what we will do here is that we will call sort, which is implemented using insertion sort, and that's the reason why I was talking about it. So since we are sorting the entire range here, we'll sort from 0 to a.length by 2. And the other half, we will take care of that. It's going to be a.length by 2 plus 1. And this is the point where we go till the end of the array. So that's that. And then we will call merge. And if you look at the signature here, for merge, we have 4 parameters to pass. One is the array, and the 3 are, this is the left endpoint, this is the middle point, and this is the right endpoint. So here we go with a left endpoint is 0. The midpoint is a.length by 2. The right endpoint, which is exclusive, right here, is this. Now, what you got to figure out, like this is how we are calling it, and it follows the pattern that we have in Java's implementation of sorts. That the left endpoint is inclusive, whereas the right endpoint is exclusive. Okay, so I want to go with that convention, but the algorithm that the pseudocode that we are stealing from here, P and R, they are both inclusive. Okay, so we'll have to keep that in mind, and we'll have to account for that. We'll have to make some adjustments in the pseudocode in our translation process. Now, this guy is complaining because there is no implementation for merge. Yeah, so go figure. We'll have to create a method for this. So we can have private void merge. This is the array, and I hate to do this, naming a variable, or here in our case, it's going to be an object, an array, with uppercase. We shouldn't be doing that since it's Java, but I just want to keep it closely linked to the code here. So this is Q, and this is R. Yeah. By the way, I don't remember if I talked about this before. Every time I have to type Q, I have to reach out on my laptop's keyboard. See? This is what my son did. How cute is that? He took off the key Q. He doesn't like that. Okay, so that's gone. Okay, we're going to return the array. Oh no, we don't have to. No real need. Yeah, we can leave it as void. Now, one thing I should do. Yeah, the complaint is coming from the other one, where we are supposed to return the array. So that's what's the complaint about. This is where we should return the array, because that's how I wrote it. Now, in an ideal scenario, we should be unit testing merge as well. Okay. So each and every method over here should be unit tested. But since we have written code for unit testing insertion sort, we can imagine that that works properly. If anything goes wrong there, that would be caught. So if we call, if you write a test for parallel sort, since both these sorts are working properly from line number 26 and 27, if we assume that, then perhaps any sort of error that we have in the code will be due to line number 28, the merge call. Now, this thing in itself, it's flawed. Okay, it's not going to work further down the line if we make changes to the sorting implementation. Maybe we will have some effect where this actually ruins the code that we have here. And that way, maybe our merge will be okay, but maybe the sort is somehow screwed up, and that is not getting caught. So we should really write unit test for merge, but I wrote a little bit of unit testing. I mean, it's not that I'm not doing anything at all, right? So I'm going to cut me a slack and start writing something here. So for the sorting service, see, we got this parallel sort written. We don't have the merge written. I'm going to try out something called extreme programming. It's not that we have to write the entire piece of code and then go back to writing the tests. They can work hand in hand. As soon as you write the header of a method, or at least the prototype of the method, you are good to write the test. And that's actually a much better thing to do. Before implementing the method, if you write the test code first, it is actually a better thing to do, because you are then guaranteed to work in a without bias and set up all your tests properly, then you keep on writing your actual code and keep on testing. You'll get test fails, test fails, test fails, till it gets to a point where you actually get all the green signals, and that's the best feeling in the world, right? I guess not, but who cares? So yeah. So we got this method called test 50 shades of gray. Oh no, it was a test sorting 50-50 array. But I want to write something else here. Test parallel sort. So what we are doing here in testing parallel sort, right now we got the same example, and I want to continue with that. And later on, we will change things around. See, right here, using arrays.sort, what we could do is we could sort the entire array. This is Java's implementation of sort, by the way. Okay. So this is something we have already taken care of. And now we have our sorting service. Rather than having sort the entire array, which is what we are going to do, right? Sorts the entire array, but so does parallel sort. Okay, so we will use that. And then we will delete this line because I don't need that anymore. So we'll see if the arrays sorting version matches with our parallel sorting version. Okay, it shouldn't work. Yeah, because, well, we have the 50-50 things done, but we don't have the merge thing in place. So right now we got a test fail, and that's as expected. So you see that arrays.sort properly sorted everything out, but here we have the left half sorted and the right half sorted, but it's not merged together, and that's why it fails, which is exactly what we wanted. Okay, so let's get on with this. Where is my merge? Right here. Okay. So I'm going to leave it on the side, always on top, right? And start stealing code from here. Now, I'll have to remind myself to adjust for zero-based indexing like we have for programming languages versus what we have for natural pseudocodes where we start our indexing from 1, right? So we'll definitely have to make adjustment for that. And also for the fact that in Introduction to Algorithm, Corman, Lisason, Riveston signed this 3rd edition of the book. This is inclusive and so is R. So P and R both are inclusive. So I'll have to take that into account as well. And the other thing that I notice is that going from the 2nd edition to the 3rd edition, I'm pretty sure they made some changes in the merge algorithm. So this is something a little bit new to me. I mean, as a student, I was following the 2nd edition of the book. And as a teacher, I did pick up the 3rd edition, yes. But not always I have to go through all these different pseudocodes and all these chapters. So this is a little bit different for me. Anyways, it's not going to matter, I think. Not so much anyways. So we got this variable n1, which is q minus p plus 1. And that's okay, because from the left endpoint to the right endpoint, not the right endpoint, the median point, if you want to count the number of elements in there, if you want to include both the indices, it has to be q minus p plus 1. So let's say I want to go from 0 to 4, 0, 1, 2, 3, 4, there are 5 elements. So 4 minus 0 plus 1, that's 5 elements. That's what we write. And for the remaining things, for n2, it's going to be r minus q. Where's q? Minus 1 in here. Because this is where this is already taken care of. Q is already a part of the first half. So that's why this one gets left out here. And now we have to create two to sub-arrays left and right. Okay, so let's do that. And the sub-arrays, they have indices going from 1 to n1 plus 1. That means altogether there are n1 plus 1 elements in the left half and n2 plus 1 elements in the right half. So the way we declared them is int L, this is an array, equal to new int, how many elements here? N1 plus 1. And for the right half, it's going to be new int n2 plus 1. Then we copy over elements from the original array A. The left half of it goes to L, and the right half of that goes to R. So line number 4 through 7 does this thing. So for int I equal to, instead of going from 1, we start with 0. I is less than n1, I plus plus, and then we say Li is equal to A, B plus I minus 1, B plus I minus 1. Here we go. And for the other half, for int j equal to 0, j is less than n2, j plus plus, this is where we do rj is equal to, what it says is a q, oh, I don't have q, q plus j, right? So that's that. But we will start 1 after q, is why we have to add 1 to that. So that's that. And we got 2 more adjustments to make. For the left half, n1 plus 1 is equal to positive infinity, which is, in our case, integer dot max value. This is going to be another one. Oh no, but this is for the right half, right? So that's that. And then we got to do a little bit more, but yeah, let me implement the whole thing, and if things don't work out, only then I want to debug. I'm getting super lazy here. So we start with 0 because line number 11, 10 and 11, they both have I and j equal to 1, which means in our case, it would start with 0, right? And then we have another loop. For k equal to p, k is less than r, k plus plus. And we do a bunch of things. What's that? Line 13 says if li is less than or equal to rj, you got to do two things. A k is equal to li. So that's that. And the else part says a k is equal to rj, right? And j equal to j plus 1. All right, I stayed true. So let me unsticky this and run this one. Not good. Not good at all. So I got index out of bounds, -1. Where did we get -1 and why did we get -1? Okay, this guy. And it makes sense. See, we started with p equal to 0. We the first call that it gets p is equal to 0. So we have 0 plus 0 minus 1. So the very first index right there is going to be negative, which is not possible. This is not Python. No, still doesn't pass. So I got another array index out of bounds, and it's not funny. Index 7 out of bounds for length 7. And this is happening here. No. So how many elements actually we got for N1 and N2? Okay, all right. This is outright stupid. Yeah. For zero-based indexing, the very last index that you can go for an array of length n1 plus 1 is n1, not n1 plus 1. I mean, what were I thinking? Like, what was I thinking, right? I hate translating code like this. Okay, so yeah. Didn't manage to pass in the first go. I had to fix all these things, but this is also a nice thing to show that if you have unit test in place, you can keep on failing, failing, failing till you pass everything. Even though I didn't fail on purpose, it was a good thing that it failed. It shows you that unit test actually works. So we have our parallel sort. Okay, it actually sorts the entire array by splitting this into two halves, and it sorts the left half, it sorts the right half, then it merges the entire thing. Does it do it parallelly? No, it doesn't. Yeah, and that's why there is absolutely no benefit of doing this in this way. And we weren't here in the session to see it do this thing sequentially. Line number 26 is a blocking call. So till it is done, we don't proceed to line number 27, okay? So this is pretty much sequential. We do this line 26, go down to line 27, then we go to line number 28. But what we essentially wanted to do, we wanted to get into parallel sort, take a branch, go into the first half, and at the same time, take another branch, carry on with working on this, and then go down with the sorting. And when this is done, only then we go into the merge. That was a stupid thing to do. Let me do it properly. I mean, I got these notes for a reason here. So what I was meaning to say is that if you want to write proper parallel sort, okay, when you get into this in a sequential call, this is where you split up the calls. So what happens here is that you call insertion sort, or sort in our case. I mean, yeah, we can forget what that implementation was. So just sort, another sort. It can be any sort, really, okay? So this can happen in parallel, these two things, okay? And let me purposefully make one shorter than the other one, saying that this one takes less time and this one takes more time, okay? But eventually, we will have to wait, right, for these two things to end. And once this is done, we will send this, both the results, to something else. Okay, and from there on, it's going to be another sequential thing. So this is what we are trying to implement, and this is why this is going to be called multi-thread. Threads are like a tiny little thing, okay, like a string, like this. This is a thread. This is another thread. Okay, this is another thread. Now, in sequential programming, you just only have a single thread, and you execute statements after statements going like this. The loops and the conditional branches you have, they are still part of the same thread. Like, I mean, if you think about looping, it's the same thread in a loop. If you think about branching, you take another branch and you continue like that. But it's not going in two paths at the same time. If you go on looping, it's not making separate instances like that. But with multi-threading, what we will be able to do is we will be able to execute these two branches, split from here, execute them parallelly. And it's not just two branches, right? I mean, we can have as many branches as we want and execute them parallelly. Okay, so that's the nice thing. How many branches we're going to create, how many threads we're going to create, well, that's a question we can answer later on because there are so many other factors related to it. If it is computationally extensive, then you are bound by the number of processor cores you have available. You can't just create all these threads if you don't have them. But if this is IO intensive, then perhaps you can create more threads than you have processor cores. Okay. But that's a different topic, a fair bit advanced topic that I don't really need to bring out here. What we want to make sure is that these two things can work in parallel, in separate threads. And before going down to merge, we can wait a bit till these two things are done, and then we carry on with this thing, okay? What we are going to use in here to write multithreading is something that was introduced in Java right from the beginning, but people don't write multithreaded programming using these low-level things anymore. Well, they can, and that's what we're going to do anyways. But what we could do now, since better frameworks are already available, we could use the executor framework to do these things in a lot more manageable way and a lot more easier fashion. But I'm pretty old-fashioned, and this is not because of that, actually. I want to go down to the low level here to be able to work with threads. So there is a class called thread, and there is an interface called runnable. Okay, we'll be using these two things to create our multi-thread programming. Okay, so I'm going to stop this session and start a new recording just for this. Oh, I can end meeting actually. So I'm hoping that this would be the last session for me trying this out. We will parallelize this thing and see if it gives us any better performance. So that's one thing to notice. And yeah, that's that. But before we get there, I want to work with random data as well, because I've been working with static data. And just one example set, maybe there are some limitations in there which I didn't really notice. So having the data generation service to generate something random would be a nice thing, a nice touch. We'll do that. But the very first thing that I said in the session that I recorded in the afternoon was that we will do this for many different data types, right? And that's what I wanted to do. But it's taking far too long, and I will do that, but let me do that tomorrow. So it's going to be a two-part series, and coming to this point, this is what I realized. This is probably not the right thing to do. So I will work with this integer example from here, and then hopefully we'll get some performance boost out of it by using multithreading. And when we get back to this problem tomorrow, we'll try to fix this thing or make changes in some certain way so that it works for generic. It can work for any data type, right? So whatever we have written, it can work for any data type. That's what we will take care of in the next session tomorrow. But for now, let's jump into the code and see what are the things we can do. So the first thing, before I forget, is to make sure is that we write some more tests with sorting service. Now we have tested this parallel sort, but it was done with static data, and it doesn't really give me enough confidence, I guess. So this is going to be a test parallel sort, but with random data. Yeah, all right. And this is the place where I'm going to change this. And before we go any farther, where are we? Where's the sorting service, right? Let me pull these services right up on top. Although this is probably a nice place to put it in terms of refactoring. I mean, putting it there where it's getting used first. I think Martin Fowler said something along that line, but I'll deviate from that. Okay. So we got this data generation service, and instead of having random data, which we always have, all our examples, the test cases were built on this tiny little set of 11 numbers. So rather than doing that, let me get data generation service to get a few more entries, like 15 of them, right? So let's just run all the tests and see how good, bad, or ugly it gets. So, oh, did we pass? No, we didn't. Okay. All right, this is not good. So this is the initial array, and what's happening here? Yeah, coming down to this point. This is where it fails. But this is our parallel sort that fails. So we have to dig into this parallel sort thing. Did we do something stupid? Or I mean, I did something stupid. I could, yeah. You know what? I actually did. And this is actually leaving some more bugs in here. But yeah, we'll have to look into this later on. Let me leave a note to self. All right, so this is just a small note that I wanted to leave for myself to make sure that it works for 0 elements or 1 element, because we may go into array index out of bounds since I'm doing this. The reason why I added +1 is that if you remember, I followed Java's convention. Okay, so the left endpoint is inclusive, but the right endpoint, it's exclusive. It's left out. That is how, if you look at the midpoint, that is always getting left out. So if for some reason, if you have the midpoint, which is less than the one element before, they will never get swapped. There won't be any comparison with that. So definitely that bit was wrong. So it has to be taken care of. But in doing so, in adding +1 to that, it may cause me to go into index that's not defined for me. And that's why I need to make sure that it actually works for 1 element, and also let's do one for 2 elements. Okay, so we'll have to write some tests for that, which I'm not going to do in this session, but I will do it anyways later on. Okay, so that's good. Now it passes all these things, but let us try this out for a little bit larger size. And so let's say 100 elements. Yeah, so it checks out. Okay, so we can work with parallel sort with random data. That's fine. It's a good thing. But we want to test it for performance. Okay, that's a real target. And when we test for performance, I think if we test it for performance against arrays.sort, it's probably not going to be a fair comparison, because they're using really efficient implementation of, so far as I remember, it was a quick sort. Okay. And if I just want to do it with insertion sort by splitting it into two halves and looking at the comparison, it definitely isn't a fair one. Okay. So rather than using arrays.sort to sort it, what I'll do here is I will use our data generation service.sort. So it's going to be the insertion sort to sort the entire array. No, well, what am I writing? Data generation service doesn't sort anything. So the sorting service does. We're going to sort it using our sorting service, but this is an implementation of insertion sort. It is going to take time, right? So if it's a single core doing all the sort, it's going to take time. The argument is that if we can somehow speed up the process by splitting the task into two halves and see it from there, then that would probably be a better comparison. But in order to do it, excuse me, in order to test it for performance, we'll have to work with a lot of data. And when we do that, if we print out the entire array, then the print itself is going to take more time than the sorting because it involves console I/O. So I am going to ignore those things, but I will write some extra code that will allow us to track how much time it takes. So I've done this before, right in this session. We'll have start and stop. Start will be equal to system dot current time millis, right? So this is our first timestamp that we are tracking, and stop will be another one, system dot current time millis. And once we have that, what I want to print in here, I'll say sequential with a Q, right? Sequential sort took percent, let's say 4 digits after the dot, F seconds. So how much time we had to wait for it to sort with sequential sort. That's what we are going to print here. And the way we do that is by writing stop minus start divided by 1000. Okay, and it has to be a floating point thing. This is something like a formatted printing, and that's why we have to use printf, not println. So this is for sorting service, and we got start and stop here, right? And we are going to do pretty much the same thing for the parallel sort. So instead of calling sequential sort, we'll say parallel sort took some certain time, right? So this is going to be that here, but we need another call. So we got start and stop, and everything is here. We're not going to print the entire thing, but we will have some idea. So let me start this with how many elements we got? We got 100 elements. We will start with that, but soon we are going to bump this up and try it for a few times to see how this is performing. Okay, so parallel sort for performance for 100 elements, we see that the parallel sort actually took more time. And this is actually okay, because if you look at the sorting service, parallel sort is not doing anything in parallel. It's all sequential till now, because we haven't introduced multi-threading yet, all right? So that's one thing. We are soon going to make changes there. But the other issue here is we are not giving enough data, and it's not a fair comparison yet. Even for sequential sorting, I need more data to do something conclusive. So let me try with 100,000, because previously when we ran it for insertion sort, I think it took around about 5 seconds or so it's not always going to be 5 seconds. It depends on the data itself. But yeah, let's give it a try. Right, so this is for performance. And you see that all the other tests have run. It's just that the last one is still lagging behind. So sequential sort took like 6.1210 seconds, whereas the parallel sort took what? All right, now I'm totally lost. Let's say we got a random array of 100,000 elements. And we copied it from random to sorted. All good. Then we are calling sorting service.sort. Let me see what that does. It's an implementation of insertion sort that gets called. Okay, so that's fine. So we're sorting the sorted array after copying it here. And we're doing this sequentially, no problem with that. And that's why it takes more time. And then we're calling parallel sort. Okay, it actually does make sense. Even though you don't have parallel implementation, it still makes sense, sort of. Because what happens here is that instead of dealing with 100,000 elements, you're actually dealing with 50,000 elements. And that takes less time. So let's take it for another spin. Okay. So yeah, like a sequential sort, even for a smaller size, it's going to take less time, right? What happens for parallel sort, even though it is not parallel actually, because these two things, they're not working in parallel, but they have to work with less amount of data. So if you think about big O of n square, when you run it for the left half, it has half the size of the array, so it's going to run a lot faster, and it's going to do that for the other half as well. And since it can do that for these two halves, and then we have a merging process which runs in linear time, this will run faster even without proper parallel implementation, is what's happening here. Because I don't remember writing parallel code yet. No, I didn't. So yeah, even with all these things, it's actually running faster. Now, this is kind of a little odd, but let me save my code, okay? This oddity, I want to save it as V1, version 1, so that I can run this thing again. What I really want to do here is I want to have a real feel of parallel programming. And these two things, I want them to run in parallel. Right now, they're not running in parallel, although they're running faster, okay? So yeah, What we can do to make sure that they run in parallel, what we got to do is we have to create threads. Now, the thread class in itself has a method called run because thread implements runnable, and runnable method has a public void run method. Now, one way of doing this, I'm not saying that this is the only way or this is probably the best way. No, I'm not saying that. Let's create this left thread. All right, so we will have a left thread and we'll have a right thread. We will run them parallelly by calling a thread.start method. But here, I want to write the implementation of the run method. And that's why I have instantiated this already, but I want to replace a part of it, the code of the thread class. And we can do this in Java right here. Right when we are instantiating this, we can write code right here. This can be done more elegantly now with the addition of functional programming, but this is something we haven't covered yet. So we will address that in a bit. Here, I want to override methods thread for the left thread. And I want to override the run method because the run method actually says what has to execute in parallel. Okay, so we are going to replace this part. So this is for the left thread. And as you can imagine that we'll probably do the same thing for the right thread. So let me steal this bit so that I can put everything together. And we are going to call this the right thread. All right. Let me refactor the code, not refactor, reformat the code so that everything lines up nicely. And before we get to this merge, what we have to do is we have to start these two threads. So left thread dot start and right thread dot start, so that these two things can run in parallel. But before we get to the merge part, we have to make sure that the task for left thread is finished, and also the task for the right thread is also finished. This is what I was showing, that before you merge, you have to make sure that you wait till both these things are done. And in order to do that with threads, what you do is you join. All right, so you have a main thread that's running, right? And the other branches are created, they're running as well. Now you're going to join this thread with the main thread and keep on waiting till this is done. And the main thread wouldn't proceed till that. Because if it does, then the merge will get called before left thread and the right thread, they're done with their job. So yeah, we call join here, but if you call join, then you'd also have to take care of interrupted exception. And the reason for that is someone may interrupt your thread. What do you do? Like if you have unfinished job, how can you handle this? All right, so right thread join, we got left thread and right thread, we join them both. We are waiting on them. When they're done, everything will be taken care of. So this is the parallel sort, and the V1 thing, we're not running that. Let's see if it speeds up the process. Like we already have speed up, and it's not going to be a fair comparison, but let's see this anyways. So the sequential one, again, is going to take time. So 5 seconds or 6 seconds, it's going to be something like that. So 6.33. And yeah, the parallel one. It runs about pretty much the same thing. It didn't really speed up the entire process, but yeah, here we got something here. So tell you what, it's getting too late for me, and I wanted to dig into this. This is a really odd kind of behavior, so to speak. Even with the performance boost, looking at the smaller size array that it has to sort, it is kind of odd for me to accept this as it is. So what I'll do, I'll run this a few more times on my own and look at this, and I'll also do a comparison with V1 and see what's happening, what kind of performance boost we got out of this parallel implementation where we have multi-threaded calls. I'll do that and see if I have a good answer to come up with. But for now, I will still upload the video because I had to take a lot of breaks in between, and it's getting just too late. It's already like almost 10 o'clock. So yeah, that would be it for this first part. Let me take some time by myself to debug this a bit, to run it a few more times to make sure that everything's fine. And for tomorrow or day after tomorrow's session, I'll talk about generics, and I'll talk about the test that I ran, and also the note to self that I left myself. I'll take care of that as well. Okay. All right. So yeah, let's stop right here. Let me stop recording this. Oh, stop the share and end this session. So please give this a try. I know I went through a lot of things to talk about a really simple thing, but yeah, I think it did cover some of the fundamental things that we always do, like unit testing and other stuff. Okay, so let me end meeting for all.